Okay, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. So please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Ishan Khurjekar, who is a PhD candidate in the Electrical and Computer Engineering Department at University of Florida, advised by Professor Joel Hawley. His research interests include probabilistic machine learning, uncertainty quantification, acoustic signal processing, structural health monitoring, and surrogate modeling. Ishan holds a master's in electrical engineering from Texas A&M University and a bachelor's degree in electronics engineering from BITS Pilani in India. Today, Ishan will talk about uncertainty-aware guided wave structural health monitoring using ensemble learning. Now, without further ado, let me pass the baton to Ishan by asking a random question as usual. That is, today's random question, let's try to be fun. What is your supernatural power if you have any?
Sometimes I have the tunnel syndrome. I don't understand what is happening in my surroundings when I'm trying to focus on something. I think a lot of people might have that, but that is something I think that's unique for me.
Very focused when you don't
Yeah.
hear any. Okay, so my daughter has that power as well. All right, thank you. So stage is yours.
Hi. Thank you, Youngsu, for inviting me today. I'm very excited to talk about my research today. And so let's start. I'm going to be talking about uncertainty-aware machine learning for structural health monitoring. So here's a brief outline of what I will be talking about. I will introduce what structural health monitoring means. I will talk about guided wave sensing approaches for SHM. Then I will talk about damage detection and damage localization approaches and what are my contributions. And finally, I will conclude this task. So I hope that all of you find something interesting, learn something new today from this talk. So structural health monitoring, why is it important? Why should we care about it? In recent times, we are using a lot of buildings, aeroplanes, bridges, roadways, etc. And this has led to a necessity to monitor their condition. Traditionally, we have non-destructive testing methods where a person actually goes and inspects those structures, but this needs a person to be actually doing that inspection, and that is costly and time consuming. So another approach to this is called as structural health monitoring, SHM in short. And what is SHM is you have an array of sensors that is permanently mounted on this structure. And then based on the received signals, you apply some signal processing techniques to detect the damage, that is tell if there is a damage in the first place, and then localize the damage, find the location of that damage. So uh, even though there is a lot of research on structural health monitoring, why is it difficult? We see a lot of research that is not translated into actual industrial applications. So what are the challenges that we have here? Most importantly, uncertainty. So no matter whatever application we have, there is going to be some uncertainty. That could be uncertainty due to the sensor noise or due to some incomplete knowledge about the underlying physical process. So I like to go with this kind of distinction. In scientific application, you need to understand the uncertainty. So let's say you're studying certain physical phenomena. You need to find a way to quantify what is the uncertainty in your variable of interest. Whereas if you're working with engineering applications, you need to manage the uncertainty. That is, let's say you're working with some system, you want to ensure that the system performs reliably even when there is uncertainty. So what happens in a sensing application? That is, you have a setup of sensors that are placed, and these sensors are recording some signals. You need to analyze something from those sensor signals. So you have this uncertainty at the sensor level. You also have the uncertainty at the output level. So my point here is, no matter whatever our research areas are, we have to deal with uncertainty. And how we deal with that is based on our application of interest. And in my presentation, I will talk about how I am working with uncertainty in my research area. So with that, let's talk a bit about guided wave sensing. So guided wave setup is a popular approach for structural health monitoring. And what it is basically you have a structure, there is a damage at some point that needs to be identified. For that, you place an array of sensors on this structure, and these sensors then transmit and receive guided waves. And based on the received waves, you do some signal processing analysis to either detect damage or localize damage. So the received signals at these sensors are a combination of two signals. So one is the direct signal that is traveling directly from the transmitter to the receiver, and the second is the damage signal that is traveling from the transmitter to the damage and then to the receiver. So for the application, what we need to do is subtract away the baseline, that is the direct path signal. So we are only left with the damage signal. And the advantages of using guided wave setup is it is sensitive to damage. It also has a large scanning range, but there are certain challenges too. The underlying physics of wave propagation is complicated. You need to be developing the appropriate mathematical models to deal with that. Secondly, you also have external variations such as snowfall, rainfall that lead to temperature variations, and this also affects the wave propagation. So the common model used for guided waves is called as a Lamb wave model. It was developed by a British mathematician physicist, and the x, that is the frequency domain representation, at a particular frequency omega and at a distance r, is given by this summation over n wave modes. So every wave mode can be considered as a distinct signal component. So your wave is made up of multiple such wave modes. And the term that we see in the square root, the kappa, that's the wave number. So the kappa is dependent on the mode n and the frequency omega. So this wave number frequency relationship is captured in the dispersion curves, and this is why the wave exhibits dispersive behavior. So it can happen that at a particular frequency, the wave is traveling in two different modes. And the wave velocity can also be calculated by the inverse slope of the dispersion curve. So on the left side, we see dispersion curves. So I have illustrated two modes here, S0 mode and the A0 mode. Those are the prominent modes that researchers work with for guided waves. And these lead to the simulated waveform that we see on the right. You see the S0 mode occurring first, followed by the A0 mode. And this is what a typical simulation of a guided wave looks like. So remember I mentioned briefly the need for baseline subtraction. So here you will see on the left, it's a signal without any damage. On the right, you have a signal with damage. So you will see that the damage signal is really incoherent or small. Uh, and that tells us that we need to be really doing baseline subtraction if we want to use this for damage detection or localization. So with that background, I'll talk about the first task that I have tackled, that is damage detection. So Why do we need to do damage detection early on? That is because it can reduce structural repair cost in the future. It can also avoid catastrophic failures. The only big real-time requirement is it should be robust to the external variations such as rainfall, snowfall. It should be able to give a good detection performance in spite of these external variations. So the first challenge that we have with this is there is a mismatch between what the mathematical model tells us and what the actual experimental data looks like. On the left side, you see a simulated waveform from the lab wave model. You can see the S0 and the A0 modes pretty clearly in the simulated waveform. But on the right side, you see actual experimental data, and you'll see the S0 mode is almost absent. The A0 mode is there, but you also have an extra reflection. And this comes because the experimental data is generally taken from a structure with some boundaries. So you have these reflections coming from the boundaries. So this is the first challenge that we have with guided waves. There is a mismatch between the theoretical model and the experimental data. The second big challenge we have is that of the temperature variations. So what we are seeing here is an illustration showing two waveforms at two different temperatures. So as you can see later in time, there is a marked difference between the two waveforms. And this is a big source of challenge or some something we need to overcome for our damage detection. So typical strategies for dealing with temperature, they all occur at the baseline subtraction stage. So one is you choose a baseline signal from a bank of baseline signals taken at different temperatures. Another approach is you stretch the observed signal to match a baseline signal. But these are all at the baseline subtraction stage. And the typical approach to guided wave damage detection, one is you can use an energy-based method. That is, you compare the energy of the two signals and threshold it appropriately to give a detection output. You can think of damage detection as a binary classification damage. There are also likelihood models. That is, you train, let's say, a machine learning model for doing damage localization based on Gaussian likelihood, and then you threshold the likelihood to also give a detection output. But researchers have shown that likelihood models can also assign spurious values to out of distribution inputs. So we ask the question, can we cast damage detection as an anomaly detection problem? And what we have is an approach for robust guided wave damage detection. So the first point we have is ensemble learning. We train an ensemble of variational autoencoders that are initialized randomly to enable robustness to the temperature variations. Second point is adversarial training. We train on simulation data with adversarial perturbations to the wave number, that is the dispersive property of the wave. And finally, the variational autoencoder, using that, we can cast damage detection as an anomaly detection problem. So some more details about using a variational autoencoder. So we train the VAE on baseline subtracted data. So that is, let's say you have a structure with some damage. When you do baseline subtraction, ideally you are only going to be left with the damage signal, and that is what we consider as in distribution. And if there is no damage after baseline subtraction, there is only going to be noise, and the noise signal, that is the no damage signal, is out of distribution. And the detection statistic that we use is the output of the variational autoencoder, that is the elbow value. We take its average over all the ensembles and normalize it by the output dimension. So the output dimension is, let's say, the number of time samples times the number of sensor pair signals that we have. So this is a normalized value or detection statistic that I have at the output. And this is a figure showing the entire setup. I know there are a lot of things going here, so let me try to break it down. On the very left, we fix the simulation parameters, that is the location of the sensor array, and we use the Lamway model in this blue box here, that is the simulation engine. We pass the data through some signal processing, and we do some signal processing, some filtering, we do baseline subtraction, and we generate random damage locations over the plate dimensions, and this helps us to generate a data set of damage signals, and this forms the training data. And similarly, we have an experimental setup that is shown in the orange box here. That is, we observe the data over the sensors, we do some filtering, the baseline subtraction, and we store that as the test data set. And finally, the training data is inputted to the ensemble of variational autoencoders. And after the training process, we get this detection statistic, that is the normalized value of the loss function of the VAE. So here is a architecture of the VAE that I use. So compared to computer vision tasks, this is a shallow network, but we have found that this works the best for our task. We have two 1D convolutional layers at the start, followed by a dense layers. And then in the decoder phase of the VAE, we have the transposed of the 1D convolutional layers. So coming to the experimental setup, we have this plate of aluminium of dimensions 1.2 times 1.2 meters, and this is exposed to non-uniform temperature variations. So what we do is place a heater at some point on this plate, and that creates non-uniform temperature variations. And the red diamond that you see here, that's the damage location. We collect 77 measurements over a duration of 6 hours, and the damage is simulated by placing a mass that has the same scattering effect, and it is placed from the 37th measurement onwards. So you have some no damage samples and you have some damage samples from this experimental setup. Now coming to this topic of how can we quantify the effect of temperature, at least approximately. So typically researchers have approximated temperature effect as a time stretch operation. So if we consider two signals x of t and s of t recorded at two different temperatures, s of t can also be written as x of alpha times t, where alpha is some stretch factor that needs to be estimated. And the optimal stretch factor is the one that minimizes the residual energy between the two signals at two different temperatures. And the stretch factor is computed using the scale transform, which is a variant of the Fourier transform. And one interesting property about the scale transform is uh, the time stretch. A stretch in the time domain is equal to a phase shift in the frequency domain. So this is similar to the Fourier transform property that a delay in time domain is equivalent to a phase shift in the frequency domain. So here is an illustration showing the effect of temperature variations. So here we have plotted the correlation coefficient against the stretch factor. So this is plotted for three different signals against one reference signal. So if we look at the x-axis here, the range is 0.998 to 1.003. So, so this range of stretch factor corresponds to temperature variations of 4 degrees to 19 degrees Celsius. And you can see that as the stretch factor deviates from 1, the correlation coefficient starts dropping substantially. So this graph or this figure illustrates what is the effect of temperature variations on the guided waves. So finally, the detection performance that we see with our ensemble variational autoencoder approach. This is a histogram showing the distinction between the damage and no damage cases. So we see that the two distributions for damage and no damage are well separated, signifying robustness. But what about some numbers, the actual performance of the detection method that we use? So we compare these four methods. One is an ensemble of variational autoencoders trained with adversarial data. Second is an ensemble of VAE trained on ideal data, that is without any adversarial perturbations. Then we have the likelihood model, that is a model trained for some other localization task, for example, that is then used for this detection. So we see that the probability of false alarm, that is you have the model predicts that there is a damage when there is actually no damage, that is the probability of false alarm. So both the likelihood models here, they have a very high probability of false alarm, and that is what researchers have shown too, that likelihood models assign spurious values to out of distribution inputs. And the first two rows here, that is the ensemble VAE approach, show a very probability of false alarm is 0. But you can see that when we train the VAE with adversarial data, we have a high probability of detection. That is, the network says there is a damage when there is actually a damage. So we see that the VAE ensemble approach, when trained on adversarial data, has superior performance. So that was all about damage detection. Now we move to the next task in structural health monitoring, that is damage localization, actually finding the location of the damage. So traditional signal processing methods have tried to solve this inverse problem as by solving multiple forward problems. So what we have is the sensors are collecting some measurements and you need to estimate some unknown quantity, that is the damage location, from these measurements. So we have a mathematical model, and by solving this mathematical model at every grid point, you then correlate that with the experimental data. So the point that gives the highest correlation between the mathematical model and the experimental data is the estimated location. So on the right, we have a figure called as a ambiguity surface. So that's basically a heat map of the correlation values. And this is to be noted is in ideal conditions. So in these conditions, you can see that the correlation value is actually highest for the actual damage location. So this shows a good performance. But what happens in presence of the temperature variations? It affects localization performance substantially. So in this figure here, we can see on the top, that's ideal conditions. That's when the localization performance is good. But when we have environmental variations, temperature variations, the localization performance drops. We can see that this region of high correlation is diffused. It's not close to the actual damage location. So we can see that the localization performance is affected by the temperature variations. And as we discussed before, there are certain temperature compensation methods, such as choosing the right baseline, stretching the baseline signal, but all of them are at the baseline subtraction phase, and they do not address the effect of these temperature variations on the localization algorithms. That is, maybe I want a metric of uncertainty in the output location. How do I get that? So that is one more challenge that we have with localization. With that motivation, we ask the question, can we use deep learning for guided wave damage localization? One potential uh, positive point is that deep neural networks have been shown to learn for a variety of scientific and engineering tasks with complex or complicated input data. And deep learning systems can be used in test time with a single forward pass. You can train the data, you can train the network offline and then just have it predict using a single forward pass in real time. So that is one more advantage that we have with deep learning. But there are challenges, and those are very critical challenges for this task. So the first is any deep learning application needs as much training data as it can have, right? So, but here we have the challenge that we only have limited experimental data sets. We cannot go around creating new specimens and then breaking them with damages. So that would take a lot of time and efforts. So we need to find a way to bypass that challenge. And then the second challenge is these temperature variations that we have seen affect the detection and localization performance. There needs to be a strategy of dealing with those external variations. We need to show robust performance even in the presence of those variations. And finally, as an effect of these external variations, there is also going to be uncertainty at the output. So how can we build better methods that can express the output uncertainty, quantify the output uncertainty? So if a deep network was trained in an end-to-end manner, this is how it would look like. You have this input signals at the input. So we have this guided wave signal, and now it's not just one signal. You have the signals coming from all the sensors. So you have multiple signals that can be inputted to a deep network, and that gives a location prediction by minimizing the distance between the true and predicted damage locations. So this is what a typical deep network process or framework would look like. But we have these challenges that we also need to show or visualize the output uncertainty. And for that, we propose a framework where we train on simulated data alone, simulated guided wave data, and test on experimental data. We also enable robustness to the temperature variations by using an ensemble approach. And finally, as a result of this ensemble approach, we can also quantify the output uncertainty as the ensemble standard deviation. So here is a similar figure for damage localization. So as before, in this blue box, we have the training data generation process where you have the LambWave simulation engine that is generating data for us. And for every data point, you have a random damage location. We do filtering, we do baseline subtraction to get the training data set. Similarly, we have the experimental setup that gives us the experimental observations, and then we train this ensemble of neural networks that can give us the final damage location prediction and also the localization uncertainty. Here is a table showing the network. So the input is, like I said, a matrix of size, let's say Q cross M, where Q is the length of the signal and M is the number of sensor pairs we are using in our setup. So typical sizes for my experiment would be 1000 cross 56. That would say the length of the signal is 1000 and I have 56 sensor pairs. So 8 sensors can lead to 8 into 7, that is 56 sensor pairs. So those are my typical input sizes. And then I have two 1D convolutional layers and then 4 dense layers. And finally, the output, which gives the damage location. To compare my approach with the existing methods, we have two approaches. So the delay and sum imaging, called as DAS, that assumes that the wave travels with a constant group wave velocity, that is a narrowband model. And here one note is that the performance depends on the right choice of the group wave velocity, and that needs some domain knowledge. And the second method that I compare with is called as match field processing, MFP. And this uses a wideband model of wave propagation. And researchers have also modified this approach using some data-driven methods such as compressed sensing, but they need access to the test time measurements. So the comparison metrics that I have are the average localization error and the resolution, that is the half amplitude width. So basically, if you're talking about the ensemble network, I get these predictions from the ensemble network. I uh, I've I characterize that as a Gaussian distribution with some mean and standard deviation, and then I calculate the half amplitude width. And similarly for the delay and sum and match field processing, I fit a Gaussian curve to the normalized ambiguity surface or the heat map figure that we saw before. So here is a table comparing the results. So we can see our proposed approach shown in red here. It has it has uh, it has a superior performance compared to the other methods for lower number of sensors. The black box here shows the performance comparison for 8 sensors, and we can see our proposed approach has much better performance than the other methods. And similarly, our approach has comparable performance for more number of sensors. So one note here is, as I mentioned, the delay and sum needs knowledge about the group wave velocity, and the delay and the match field processing, the two DDMFP methods shown here, they need access to the test time measurements. On the other hand, our ensemble network is trained on simulated data alone without the uh, without the need for any kind of more knowledge needed. So here are some visual illustrations showing the different methods. So this figure on the extreme left and the figure next to it, those are the two MFP methods, and this is the heat map that we have for these methods, and this is with simulated data in ideal conditions. So we can see that for almost all the methods, the performance is good. The predicted damage location is close to the true damage location, that is the red box that we are seeing here. And on the extreme right, we have our proposed approach, the heat map for our approach. And then what happens when we work with actual experimental data? This is where it gets interesting. We can see that for the first three figures here, those are the traditional methods, match field processing and delay and sum. So we can see that the performance, the localization performance drops substantially. The peak is not localized, whereas we can see for our approach on the extreme right, we have a bigger region of uncertainty, but the the peak of the region is near the true damage location, signifying robust localization performance. And we also plot the localization error versus the stretch factor. So to note here again, the stretch factor is a quantification of the degree of temperature variations. So we can see that our approach, the red curve, has comparatively better performance or lower localization error for all the stretch factors that we see in our experimental data. And we see that there is no obvious trend with the stretch factor values too. And this is where we vary the size of the ensemble. And we can see that as we go on increasing the ensemble size, the localization error, that is the blue bar, it it goes on decreasing. The localization error goes on decreasing. But as we go above an ensemble size of 10, the marginal increase in performance is not too big. So that's why we fix the size of our ensemble at 10. And finally, this is where we talk about quantifying the output uncertainty. So this is with simulation data. I generate 100 test samples with random damage locations. And for each sample, we have a random stretch factor that is sampled from a range of 0.99 to 1.01. So just to remind you, in our experimental data, the stretch factor variations were 0.998 to 1.003, and that corresponded to a temperature range of 4 to 19 degrees Celsius. So a range of 0.99 to 1.01 is even bigger than that. So what we can see here is we choose the uncertainty metric as the mean of our standard deviation of the ensemble predictions. So what we can see here is the uncertainty metric plotted against the stretch factor. And we can see that for stretch factor close to 1, that is ideal conditions, the uncertainty metric value is the least, close to 0. But as we deviate from a value of 1 on both sides, the uncertainty value rises. So this serves as a good representation of, or a good validation of our chosen uncertainty metric. Here is another illustration that I have. So here I have generated a pattern in the test samples, and they are stretched according to a pattern of repeating values. So you can think of this as there's a heater at some point, and that can be toggled in 3 different conditions: off condition, low condition, and high condition. So the stretch factor has 3 distinct values: 0.991 and 1.01, corresponding to these three hypothetical temperature conditions. And the interesting trend we see here is um, when the stretch factor deviates from 1, that is when the uncertainty metric, the blue curve here, also has high values for both for deviations from 1, both in the direction of 0.99 as well as in 1.01. But when the stretch factor is close to 1 here, that's when the uncertainty metric value is also the lowest. So this is similar to the earlier figure we saw, that as we deviate from a stretch factor of 1 from the ideal condition, the uncertainty value also rises. So here are the results for the experimental data. And we can see here slightly similar trends. In the figure on the right, we have the the stretch factor that is showing an oscillatory behavior. So that is what was presented in our experimental setup, a fan that was oscillating between different conditions. And the uncertainty metric value, the blue curve, shows trends similar to before. That is, when the stretch factor deviates from 1, the uncertainty metric value is high. And when the stretch factor is close to 1, the uncertainty metric value also drops. So to conclude, what we have proposed here are machine learning networks for 2 tasks of damage detection and damage localization using guided waves. So our approach has multiple advantages. First is we train on simulated data alone and test on actual experimental data. And secondly, we have this robustness to temperature variations that can occur in a real-time setup. And we tackle that we tackle those temperature variations using an ensemble approach. We have superior performance in the lower sensor regime compared to the other signal processing methods. And finally, as a result of using the ensemble approach, we can also quantify the output uncertainty. What is next for us? We want to do a sensitivity analysis. That is, how do different factors of input variations affect the detection and localization performance? That is, I can change the number of sensors, I can change the positioning of the sensor array, I can put them all in one corner of the structure or in a random location and see how that affects the performance. And I need to do this in a simulation phase. I cannot do it on the testing phase because the time and money is limited. So how can I set up a framework for that? And finally, how can I extend this approach to different structure geometries? So in the experimental setup, I explained before, we had a plate of square dimensions, but how can we extend that to more complex geometries? And those are all the points that we want to tackle in the future. This is the work so far, or what we are currently doing. And this is our Smart Data Lab at University of Florida. All excellent researchers. And here is our PI, Professor Joel Harley, who has a lot of varied research interests. And thank you so much for listening to my talk. And I'd be happy to answer any questions that anyone in the audience has. Thank you.
All right, thank you so much for the wonderful talk, Ishan. So let's have a Q&A sessions. Anyone has any questions for Ishan? I don't see any questions in Q&A chat in chat room. Let me, while you are thinking about the questions, I can ask some
Sure.
clarification questions. If you go to slide 9, um, to- yeah, so you said in A without damage and B with damage, and basically from my eyeball norm, that looks the same uh, in terms
Yeah,
of pattern. So what do you mean by baseline subtractions? And yeah, how do you, yeah, I mean,
yeah. So this figure on the left, that is without any damage in the structure, and this figure on the right is with the damage.
yeah.
So baseline subtraction is as I explained here, the received signal at the sensor is a combination of these two signals: the direct signal that is traveling from the transmitter to the receiver, and the damage signal that is traveling from the transmitter to the damage to the receiver. So baseline subtraction removes this direct signal and keeps only the damage signal. So so this is before we do any baseline subtraction. But once we do baseline subtraction, we are left with only the damage signal. And
How does it look like, the damage signal?
so it looks similar to the lamp wave that we have here in the figure B here.
And then for that, the damaged one and not damaged ones are
Yeah,
clearly distinguishable.
yeah. So if there is no damage and we still do baseline subtraction, ideally we would be left only with noise. And if there is damage, we would see a signal like this.
Mm, I see. All right, great. Is there any other questions from audience? Or if not, I have another question. If you go to slide 11, you seems to know which one is A0 mode and which one is S0 mode and which one is reflections. As a non-expert, I cannot
Right.
tell which one is A0 mode and which one is S0 mode, which one is reflection. It looks like a A0 mode on the right is S0 mode, and then reflection is A0 mode. And
So with every mode, there is a velocity associated.
got it.
So
Okay.
yeah, so with this, so this is known by the domain experts, and you're right that it's hard for a different person to understand it. So different modes travel with different velocities. So you kind of know when to expect a particular mode based on the velocity.
Right. I see. And if you don't see the signals, then you determine that there is no S0 mode.
Yes, yes, right.
Got it. Got it. Okay. So if you go to slide 18, you said you use shallow neural net, and you found it that's the best in
Right.
in terms of what? And did you try other neural net, or what else did you try?
So, so in terms of the actual detection or localization performance, we found the networks to be of around this size to perform the best. So some other alternatives that I tried was just having a bigger network with more number of layers, or having different number of frequencies in the input, or different number of sensor pairs. So what we found out was, obviously for different number of sensor pairs, you need to appropriately increase the size of your hidden layers to be able to accurately process the all the information. Um, yeah, and I think that was the experiments that we did in trying to determine this size of the neural network.
Did you use any neural net architecture search tools? such
Um,
as
no, like,
hyper, hyper, hyper
oh,
op and
oh, no.
Raytune, etc.
Yeah.
So
S-
you might be you might want to use those tools in order to save some time for the
Right,
future.
right.
All right. Okay, there's a question by Philip in the chat. He asked, how well will this method adapt to different real systems such as aircraft, bridges, and buildings, etc.?
Yeah, that's a very important question because we ultimately want this to be applicable to some real world setup. So the experiments that we do and a lot of researchers in this field do is with a square plate or something of that sort. And it's actually a very challenging problem to be able to transfer that to some of these complex structures like aircrafts, bridges, or buildings. But there are certain transfer learning methodologies that researchers are trying to come up with that removes any kind of dependence on the structure. I mean, I could train a network for structure A and try to make it applicable to structure B, but that is something we have not tried out in this work, but we can try it later. Thank you for the
Okay,
question.
okay, sounds good. Is there any other questions from audiences? Mm, okay, if you don't mind going slide 29. Mm. All right, so basically the blue part, that's the like your physics simulation, your model simulation,
Yes,
wave simulations,
yes,
and on the top, that is the experimental
yes,
data, the orange one, and then
yes,
uh, the physics simulation use it as a train data, and the experimental data you use it as a testing, and
yes,
then you train the 10 different neural net here,
yes,
right? And then
yes,
collect all the results, and based on some distributions you try to find the mean and standard deviations.
yes, that's right.
um, but all the neural net is getting the exactly identical inputs like for the testing and training.
Yeah. So the only difference is the weight initialization of the ensemble networks. So that result was surprising to us also. That
And the neural net architectures are all the same. They
yes,
once
the only thing different is the dropout probabilities that we use and weight initializations. So one explanation that some researchers have is this ensemble approach explores different modes in the loss landscape, and that helps to achieve a robust performance.
yeah. So at the end of the day, the mean and standard deviations you quantify, that also is coming from the neural net,
Yes,
um,
yes,
the initialization seed itself.
yes.
Yeah, so I'm not sure how to interpret those uncertainty. Interesting.
Yeah, so I think we can think of the uncertainty as the conditional uncertainty, right? So given given this input, we have this output with so and so probability or the standard deviation.
Yeah, but those inputs are all the identical and architectures are all the identical, except
Right,
the
right.
initial guess for the all the neural nets. Yeah, so you're kind of trying to um, to quantify the uncertainty in neural net training in some sense.
That could be one way of looking at it. So I
Yeah.
think what you're trying to get at is, can we actually get the input uncertainty to propagate to the output?
Yeah, exactly. Yeah.
Mhm.
Yeah.
So
Okay.
we have
Yeah.
this adversarial perturbations at the input that simulate some of the temperature variation behavior.
Mhm. Mhm. Yeah, that actually, if you do that, then you may include the uncertainty. I mean that when you quantify the uncertainty, you are accounting those uncertainty. But this very setting, I think you're only quantifying the uncertainty from the neural net training.
Mm.
All right. Is there any other questions from audiences? That was all the questions I have. Well, I mean, another comment I would make is another project I'm very involved right now is the earthquake source location detection
Right.
problem. So there, we try to simulate the real earthquake thingy with the simulation, and then generate the data. And there's just some sensors on the ground, and we measure those displacement, velocity, etc. And then using only those sensors measured data, we try to find out the location of the Earth, source location. There we use the machine learning technique. We haven't quantified any uncertainty. It was all the deterministic way. I
Mm.
think some of your methodology is applicable to earthquake project I'm working on right
Yeah,
now. So
definitely.
that is
We
so that
could
is
talk some
great.
more.
That is great. All right. If we do not have any more questions, let's thank our speaker, Ishan. Thank you so much for the wonderful talk and giving a talk. I understand that you will have the defense, your PhD defense next month, right? So good luck with that, and I'm sure you will pass, right? All right.
Thank
Thank you,
you.
Ishan. Thank
Thank you.
you,
Have a
and
good
thank
day.
you. Bye.
Bye.
Thank you everyone for joining. Oh, um.